All right, and we are live. Thanks everybody for joining. My name is Luuk Hennen. I'm the CEO of EngineeringTrainer.com, and welcome to this latest live stream of Engineering Trainer TV. And today's a little special since we are welcoming Johan Bosselaar, who is actually a colleague of mine at EngineeringTrainer.com. Johan, welcome to the stream. How are you doing today?
Yeah, thanks for having me on the stream. It's nice to be on the other side of the screen for once.
Exactly.
And yeah,
So
looking forward
Johan and I
to
have
it.
been discussing a lot of technical subjects related to the courses. Johan, being the content director here at Engineering Trainer, connects a lot with specialists and produces these courses, produces some of the courses himself with the team. And we thought to just take one of these streams and just have one of the technical discussions that we typically have within the team to have that as a live stream. So today we'll be discussing the subject of thin versus thick walled piping calculation differences. And before I continue and show you a little bit about the context of that subject, I want to invite you to join the chat. So, from wherever you are logging in, whether you came directly from YouTube or from the LinkedIn event, please make sure that you have access to the chat. It should be top right in your YouTube viewer. And let us know from which location you are logging in. It's kind of a tradition at these live streams that all viewers, let us know from where they are logging in. So please do. If the chat doesn't work, I think it's related to you have to subscribe to the channel in order to be able to participate in the chat. So consider doing that, please. And I also invite you, as always, to connect with me on LinkedIn or with Johan on LinkedIn. If you have any questions about the subject or just want to start a conversation, feel free to do so. The topic of today is related to a module that Engineering Trainer recently released, which is freely available to any of you. Johan, can you make sure that I share my screen?
Yeah, I'll make sure you share a screen. Wait a moment. Yes, there it is.
All right, perfect. So for all of you, we have the links in the show notes, but you can find this module, thin versus thick walled piping, which is freely available on our website. Browse to engineeringtrainer.com, and if you then search for the thin versus thick walled piping module, it's one of the free products in the shop. And you can just enroll, and go to your account, your dashboard, and from there you can, once you opened your courses, you can open the thin versus thick walled piping module. And this module is actually it has a little bit of a different look and feel. We have integrated several videos into an interactive format with questions and slides passing by. So it's really make sure that you have to be actively involved when doing this this module. And the module itself is, I would say, like a 1 hour. Johan, would you agree?
Yeah, so it's a bit 1 hour. Yeah, if you're doing it on a slow pace, I guess. I think if you're fast, you can finish it by 40 minutes or something. So there's a lot of exercises as well. So depending on how fast you make these exercises, I think you can do it in 40 minutes, maybe an hour, something like that. Yeah.
All right. Yeah. All right. So that's a good time spent for the learning objectives. And this module is actually part of the pipe stress analysis course that starts on October 4th. Which is a course that consists of many of these modules, these interactive learning modules, combined with instructor-led live sessions. So that's the context of the topic that we are and the product that we will be discussing today. Again, the links are in the show notes, both in YouTube as in the LinkedIn event. And for now, let's head over to the actual content. Johan, maybe you can kick it off.
So let's talk about it, right? So let's see what the course, what this lesson is about. So this lesson we will discuss like what a thin wall pipe is and what a thick wall pipe is. So there are differences between them. For thin wall pipes, different equations are necessary to do a pipe stress analysis for it. And similar for thick wall piping, there is also different equations relevant. We're looking at what is a thin wall pipe, what is a thick wall pipe, and also we're also looking at like how these are integrated in two different codes. So we're looking at the EN 13480 code and the ASME B31.3. So we're looking at, how can we do these assessments? How can we say, okay, when is something a thin wall pipe, when is it a thick wall pipe, and what's the related assessment that I have to do when designing or assessing these pipes?
Right. So just one like side note is like we are going to focus, I guess, on the wall thickness calculations. I mean, there's
today or during this live stream. Yeah, so during this live stream, I think we will not go really into the code and all that, but
exactly.
We'll just keep it general, right?
yeah. So I mean, the aim for this live session is to take about, let's say, 30 minutes. And time flies, when the conversations start going and the questions start coming. So the wall thickness calculations, that's basically the central item of today, I would say. All right, let me jump one slide. All right, so just to give a brief introduction, I think most of people that work with pipe stress have seen the equation at the top here. So the hoop stress is the pressure times the diameter divided by 2 times the thickness, and like we derived that in one of the other 3 modules, and basically what we saw there, and I think most people understand this, is that if you use this equation, if you derive this equation, a certain assumption is made, which basically is that the inner diameter is kind of close to the outer diameter, or in other words, that the thickness divided by the diameter is much smaller than 1. And only if you make that assumption, you can make this very clean, like a simple equation. But today we're going to look at, if you wouldn't make that thin walled assumption, what will happen? And as Johan and I will be discussing, things can get complicated rather quickly.
And if you look at this equation at the top for the hoop stress, I think you can also relate that to like code equations, right? So there's a lot of equations within design codes that are based on that hoop stress equation when you're like designing a piping system. So that's quite interesting.
Yeah, that's a good point. And when I started doing pipe stress analysis, I mean, this equation and derivation was quite straightforward, but it was a little bit later that I understood that basically the assumption, thin walled assumption, means that you kind of assume that the hoop stress is constant through the wall thickness, which also means that if you don't make that assumption, that it is not constant anymore. Let me see if I can draw what exactly I mean by that. Oh. Now we're jumping ahead a few slides. Let's go back. Yeah. Oh, wait, I have to be here. Yeah, my pen. All right, so in this plot, we basically see a section of a pipe here, and we zoomed into that section, which is shown, which is enlarged at the left side of this visual. And basically, because of the thin walled assumption, we basically assume that the hoop stress is constant throughout the entire wall thickness, as we've visualized here. But what you basically do is, like, technically the hoop stress isn't constant. So let's say the hoop stress would be something like this, going through the wall thickness. And basically what the thin walled assumption is that, if as long as you assume that the wall thickness is not very big, so for example, this thin thickness, then the variation, the vertical variation, is also very small. So you basically neglect that vertical variation. So that is kind of like my understanding of the thin-walled assumption these days. And as long as you make that assumption, then obviously it becomes a straight line in this visual, right?
Yeah. If it's thin enough, then you can assume it's just like a constant value. Yeah.
Right. All right. Let me switch screens again. No. Yeah, there we go.
Yes, we're back.
We're back. All right. Next slide.
So what happens when you don't take that assumption? So if you have the assumption that the wall is so small that you can assume that it's constant, the through the wall stress, then you get the PD over 2T equation. But what happens when you don't do that? So in order to see how that works, you have to divide like the wall of the pipe. You have to divide that in all kinds of very small elements, and then on each element you have to make a force balance, and that force balance has to equal 0. So the sum of the forces, because it's not moving or anything, so the sum of the forces has to be 0. And when you make that force balance, you can see it on screen. So that's quite an extensive equation, quite a difficult equation. Yeah. I would say.
Yeah, as we said, like things get complicated rather quickly once you start doing this.
Yeah. So especially when you compare it to PD over 2T. So probably if you did like a physics major, or I don't know, anything else on the university, you might have seen like longer equations, but this one's pretty extensive already.
Yeah. So the way I maybe like one note I would have for this equation is that obviously it's actually 3 equations, right, in each direction.
That's true. Yeah.
Let me just see if I can start drawing again. I mean, basically, like I'm just gonna redraw this cube. We make like a small cube in that wall. And what we basically say, what this equation basically means is that for each direction, so let's say this is the longitudinal direction, you write down what the force on this side of the element would be, and you write down what the force on this side of the element would be, and you say that those added together are 0, and you do that for each direction. So you end up with 3 equations, which is the same as this equation once you start writing it down for each of these areas. And you can obviously write it also as one equation with the gradients in here, looking like this. The full derivation of this equation and the equations that follow based on this one are part of the module. They're not like detailed, or we don't ask you to know it, but they are provided in a separate PDF document that you can just download as like background.
So if you're interested in like this full derivation, you can just see how it works and how it plays out. So we're not gonna explain in detail how you do these kind of derivations or stuff. So it's that would take too long.
That would take too long, exactly. All right.
So then this lesson wouldn't take like 1 hour, but 2 or 3.
Maybe more.
And so if you go back to the previous slide, so let's see. So we forgot a step. So so in order to get to the stress in the system, you have to rewrite this entire equation and then integrate through the entire wall thickness of the pipe. So that's how you get to the stress equation.
Right.
And then if we go to the next slide, I think there are the solutions. Yeah. So if we look at the different the different components, so we have the hoop stress, we have the radial stress, and we have longitudinal stress. So those are the three directions the stress can be in a pipe. So when we solve that equation, we get the stresses in these directions. And if we look at the screen, you can see that. So that's how we presented that as well. So there are actually two terms. So there's the first term, which is a constant term, and you can see that it's fully based on internal pressure, internal radius, external pressure, external radius. So those are constant values, of course. And then there is a second term, and in that second term, there's also a dependence on r, and r is just the radius you are in. So that's a variable term based on where you are within the pipe wall.
Yeah.
To get to these equations, you can see that we didn't have to make any thin-walled assumption, and so these equations are also generally valid. So for thin-walled pipes as well. So you can also use these equations for thin-walled pipes if you want. But yeah, you will make your life harder.
Yeah, it makes life much complicated.
Yeah. You make your calculation a lot more complicated if you do that.
I mean, only by comparing, for example, the hoop, the equation for the hoop stress from Lamé's equation to the equation we started with, PD over 2T. I mean, the difference is significant.
Yeah, you can see it. Yeah. So you mentioned it. So these equations are called the Lamé's equations. So it's they have a name. So I think that's interesting. Maybe
must be Mr. Lamé or something. I have to admit, I've.
I think Lamé was the first. It sounds a bit French, but I don't know. I don't want to fill that in, but I think Mr. Lamé or Mrs. Lamé could as well be, but has derived these equations.
Yeah. All right. So let's look into these equations in a little bit more detail. So as Johan already stated, we have the constant term, the first term, and we have the variable term, which is the second term. So let's see what that would look like if we would plot it. Again, we have the wall thickness here shown, and these images all reflect a situation where the internal pressure is higher than the external pressure, right? So what that would result like for the hoop stress is that we have a high hoop stress at the inner radius, and then once we progress through the wall thickness, the stress actually drops with a curve related to 1 divided by r squared, right? So if we look at the radial one is compressive. As you can imagine, I mean, we have pressure on both sides pressing against the metal. And again, we have a constant term and a variable term. And again, the variable term has a curve that is related to 1 over r squared. And in that case, it would look something like this, as shown in this visual. Next is the longitudinal, and the longitudinal only has a constant term. So the longitudinal stress is indeed constant throughout the wall thickness, regardless of whether we're thinking about a thin or a thick-walled pipe section.
Yeah. So what I find interesting about these equations is that, like the hoop stress and the radial stress, these two equations are like almost the same, right? So the only difference there is that in the hoop stress equation, there's a plus sign in the middle, and in the radial stress equation, there's a minus sign in the middle. Like everything else is exactly the same.
Right, fair point.
So in that sense, the radial stress, I believe, doesn't have to be compressive. So if the constant term is high enough, like because the constant term is positive, the second term doesn't have to make it so that it's compressive.
Right. You mean,
Yeah.
so what situation would provide that, like if we have like almost vacuum or something in the pipe?
No, so the first term is positive when the internal pressure is higher than the external pressure. So you can see that in the first term. So you can see pi, so that's the internal pressure times the internal radius minus the outside pressure times the outside radius. So if the internal pressure is high enough, then that term becomes positive. So that term would be positive then, and then so if and the second term could make it negative because it's in the radial stress it's minus again the pi minus po. So that's if the internal pressure is higher than the external pressure, then that term becomes negative. So you don't really know if it's compressive or tensile, but
that would be worth looking into, maybe in another stream. Like, what can we find a situation and what are the conditions? If
that could be interesting. If you really look at it, if you say like the external pressure is higher than the internal pressure, then everything shifts, of course. So then the first term becomes negative. So that definitely becomes negative. And the second term becomes negative also for the hoop stress. So then actually this entire graph to the right will be flipped upside down.
So you would have
thing becomes compressive.
Let's see, compressive with the highest compressive stress on the inside, and then a reduction to a compressive stress on the outside, in case the external pressure is higher than the internal pressure. What I also find interesting is that this hoop stress, so the maximum hoop stress, the absolute value of this, is the maximum stress of any of these components. In if you consider any case, basically. And technically that would also mean that if you would bring the stress up to the limit, so reaching, let's say, the proportionality limit or like yield stress, you could have a situation where you could have some yield stress some yielding all the way at the inner side of the wall. I mean, that's just a thought, but this is basically the limiting element. I guess that's something to take away here.
It's interesting.
All right, let's move ahead to this visual, Johan.
Let's see what this entails. So again, we show here like the thin wall to the left and the thick wall piping to the right, so to the left we also see the thickness calculation. So that's the PD over 2T, or PD over 2 sigma in this case, because we rewrote the equation. And you can also do the same for the thick wall piping, and then you can see that the equation for thickness looks like that, like you see on the right. And you can see that the components are similar, right? So you can see that there is a D over T term in both equations.
D over 2.
Oh, sorry, D over 2. Yeah, thanks. And there is a term that's based on sigma, and so the stress and the pressure. And for the standard equation for thin wall pipes, it's P over sigma, and for the thick wall pipes, it's a bit more extensive, a bit more difficult equation with a square root and stuff.
So in the course, it might be worth mentioning, you know, when you do the module, I think it was slide 20, yeah.
Yeah.
Here you can actually, you know, as I mentioned, we made the PDF with all the technical derivations available for background reading. And this also includes a section. Let me just scroll down a little bit.
Yeah, it's all the way down.
Yeah, here it is, to go from, let's say, the Lamé's equation for the hoop stress, so the one we also had on our slide just a moment ago, to rewrite
Can you zoom
this
in a bit, maybe?
Oh, that's a good point. Yeah.
Oh yeah, that's better. I can see it now.
Yeah. So this is the hoop stress, Lamé's equation for the hoop stress. We just saw it on the slides as well. And if you would write, I mean, it's written here in terms of radius, inner pressure, outer pressure. If you would rewrite this in terms of diameter and gauge pressure, then you would actually end up, and thickness, right? So it's all done in that downloadable slide. So you would actually end up with the equation shown on the slide. And like, we won't go into depth about that today, but that is also one of the basic equations, the base equations that is used in one of the codes for thick wall.
Yes, yeah, that's true. Yeah, so the European code, they use this equation as a base. Yeah.
EN 3480, right?
Yeah.
All right. So back to the slides.
Yeah. So and so the question becomes, when is a pipe thin-walled and when is a pipe thick-walled, right? So how do you know? You have to make like a certain point at which you say, okay, now it's a thick-walled pipe and now it's a thin-walled pipe. So what we did is we plotted like different ways to calculate the stress in the hoop stress in a pipe. So on the left axis, you can see the hoop stress divided by the pressure, and on the horizontal axis, you can see the outer radius divided by the inner radius. So the outer radius divided by the inner radius is like a way of telling the thickness, right? So on the right side of the graph, you have very thick pipes, and on the left side of the graph, you have very thin pipes. So if it's 1, the outer radius divided by the inner radius, they are the same, right? So it's the infinitely small, infinitely thin pipe would be on the left side. And what we did is we plotted 4 ways of calculating this. So there's the thick-walled equation. So that's the light blue line. You have the thin-walled equations using the inner diameter. You have the thin-walled equations using the outer diameter, and you have a code stress equation. So that's based on one of the design codes. And so you can see that so these four graphs.
Sorry to interrupt. Like maybe like the vertical axis, just to like add here, like, it's the log scale. That's maybe something to realize for the people.
Oh yeah, it's a log scale
listening, right?
Yeah, that's important.
If you would plot this, so the vertical axis is stress divided by pressure. So basically, it shows like for the same pressure, the stresses would be different for different thickness or different calculation methods. But it's on a log scale. If you would do this on a linear scale, I mean, this would all be very compressed, I guess.
Yeah, no, really far apart, right?
Oh, stretched. Yeah, you're right. Yeah. You wouldn't be able to see depends. Like any of this part. Yeah. So so you could say like, oh, these lines are very close by. So why change? Why bother?
Why bother? Indeed. But so what you can see is that like all these lines, they overlap for thin-walled pipes, right? So if the pipe is really thin, all these lines overlap. So that's great. So that's there you can say, okay, my pipe is a thin-walled pipe, right?
Yeah.
But when we move further to the right, you can see that they diverge a bit. They start diverging, and in the end, are pretty much diverged when you have an R over R I of 4, for instance, then you can see these pipes don't overlap. So then, you can't just say, okay, we use this equation or that equation. You have to use the thick-walled equation, right?
Yeah.
Or you want to have the most realistic equation, because what you can also do, so that's the uppermost equation. That's the thin-walled equation using the outer diameter. So you can just say, okay, I'm just going to use the thin-walled equation using outer diameter, and that will actually always give you like a very conservative results. But it will give you conservative results, but that means that you would have to make your pipes really thick.
Yeah. Again,
on
a log scale. Yeah.
So it's a very small difference, but it could mean that you have to increase the pipe thickness by a lot for certain pressures. So so that's why most codes use the code stress, which is normally a pretty good indicator of the stress within a thin-walled pipe. But you can see that it's in this case it's lower than the thick-walled pipe where your arrow is at the moment.
Yeah.
So that would mean that it's not conservative. So that could mean that the stresses they predict are lower than the actual stresses in the pipe. And that means that you really have to consider a different approach, because otherwise you might design a pipe that's too thin and it might break. So it's important.
So the question becomes, where do you choose which equation is relevant? So
if you look at this, where would you choose it to be?
But it's like, I mean, it would be like a visual assessment, right? So I would plot percentages in there, like differences or something first. But you would lean all the way. I would lean all the way to the left, I would guess. But that would be even for quite thin pipes. But that's just because visually, like, based on the line thicknesses that we chose and stuff.
Yeah, that's true. Yeah.
All right. So let's have a look at the different codes. So first of all, EN13480. They basically say D over D, so D outside over D inner, which is the same as the ratio of the radii, which we have plotted on the horizontal axis here, is 1.7. They say that is like the point where one switches to the next.
That's pretty thick, right?
Yeah.
So that's like 1.7. So that means that for a DN100 pipe, so a 100 millimeter pipe, you would need a wall thickness of 70 millimeters.
Yeah.
So that's quite a thick pipe already.
Yeah, that is true. Yeah. How about the B31.3? Let's go to that one. And please be aware that their definition is in a different ratio. So the thickness divided by the diameter, which is 1/6 or 0.1667. It's also often this fracture is also often written a little bit different. But be aware that we in this, like going from the previous slide, so this one, we flip we change the horizontal axis. So this is outer radius divided by inner radius. This is thickness divided by diameter. The same vertical axis, also on a logarithmic scale, the same plots, and they basically say 1/6. That's how they define it. And if you're thick-walled, I mean, in the module itself, we go into a little bit more depth about Appendix 9 of the actual code, where I believe this is being discussed. But I think key takeaways for any engineer working with pipe stress, at least those are the numbers that I focused on, is this one and the previous one, if you ever use the EN13480.
Yeah, so those are the limits that the codes provide. So I think for the EN code, it's quite hard limit. So they say, okay, when you reach this point, you have to use a different. So you have to use these Lamé equations, or at least the equations that they provide. And for the ASME code, there is a bit more engineering judgment involved. So you have to. They say, okay, you have to use a more relevant, equation or theory, and they provide it themselves in chapter 9 of the code, but they give you some space. You can choose a bit if
you can choose a different one.
Yeah, so it's not really clearly specified. So they provide the chapter 9. So
exactly.
It's logical to use that one, but it's not like written in stone. So they don't say you have to use this. They just say you can't use this anymore.
Yeah. And I also believe that you need permission from the customer, right?
Yeah. So that's also what they do. So yeah, you have to discuss with your client, and discuss. Okay, you want to use this theory instead of the thin-walled equations. Do you agree with that? And then, if they agree, then you can go
very
on.
explicit. Yeah. All right. Having stated that, let's wrap this up, Johan. So for the final slide, I thought it would be nice to just run over some of the objectives of the module that you'll find on EngineeringTrainer.com. So the first one is to know the different analysis methods of pipes of varying wall thickness. And we already showed you the thin walled assumption and the equation resulting from that, and Lamé's equation. And in the module, there will be a lot more emphasis on both and visuals and examples to illustrate those. Second objective, to be aware of the advantages and disadvantages of each method. Third objective, to know when to apply the thin or thick-walled relations during your piping design. We already showed you the limits that both codes are defining, and some of the examples and some of the nuances related to those are in the module itself. And the fourth objective of this lesson is to determine the minimum required wall thickness of thick-walled pipe. But once you got these first three lesson objectives in, the fourth will definitely be a piece of cake. I would say you've learned that by then.
Yeah.
All right. Having said that, Johan, thanks for joining. I mean, you worked a lot on this lesson and many of the other lessons of the pipe stress analysis course. I thought it was a pleasure to just do like a little bit of an informal conversation about the things that are in the module.
I had a great time. It was fun.
All right. So just to wrap these things up, I mean, for all of those watching this live or watching the video available later on, I invite you to head over to EngineeringTrainer.com, search for the free thin versus thick-walled piping module, and you can just, set up your account if you don't have one already, and you can see it as one of the courses popping up. And once you open it, you can start with the course straight away. And this, if you like this type of teaching and this type of lessons, this lesson, the thin versus thick-walled piping lesson, is part of the pipe stress analysis course that will start early October, I believe, 4th of October. So if you or anybody in your team wants to know more in-depth knowledge about pipe stress analysis, make sure to check these courses out. Links are in the show notes, as we say. All right, Johan, thanks again. Have a great day, and we'll speak soon.
Yes. Goodbye.
Bye-bye.